Okay, so I think you guys right now you can log in the system to register. Let me take a picture for you guys. Well, I think you can continue. All right, I think right now I open the files and then we restart. All right, so maybe 2 weeks ago, right? Because last week it is a day off for us. So 2 weeks ago, we reached this page, page 29. And with that, you guys know the event. Even right now, we have the departure only. Actually, we have the event of arrival as well. So with that, you know, we have the event and we try to have the description for different event, arrival, departure. And with that, you guys know how to have the update for server status. And we can have the update for number in queue. And also the others. In fact, we still have a few pages, but I think you guys can follow the discussion 2 weeks ago for the snapshot for some of the status of the system. Therefore, in the following, I will skip some of the pages from page 30 to 33. All right. So I think you can use the principle we used for the discussion 2 weeks ago, or maybe you can refer to the textbook and then you can understand the system totally. And right now, we want that you guys know the specific system. That says the current system code MM1. In the previous discussion, we simply code we have the single server queue. But right now, we have the specific single server queue. We call MM1. Look at these. we have an M. So what that means? M means the inter-arrival time. If we talk about the first M. Why? Because we try to borrow the word Markovian. If we want to have the property for such a system with the Markovian property, in fact, this M should be exponential. So we use the word Markovian, and Markovian actually achieved by exponential. So that's why the first M indicate the IID. Again, we have IID, so we have IID exponential inter-arrival times. And in fact, the same for the second M, we still have the exponential. But the second M for the description of service time. That's why M means exponential. If we use a current system to talk about M, M specifically indicate exponential. For the first M, the first position try to indicate inter-arrival times. And the second M means the service times. All right. And later we have the further detailed discussion on the notation, but we try to use M1. So M, first M, exponential inter-arrival time. Second M, exponential service time. And how about the third position? The third position, we have 1. Actually, the third position indicates the number of servers. All right, so number of servers. So that says here we have 1. So it says we have a single server. So that's why M means a single server. All right, so in fact, we have MM1. If you want to have the formal notation, it should be we have A/B/C/D and /E. In fact, we have a can down notation. All right, and we have 5 positions, but right now we have inter-arrival time. All right, and service time and the number of servers. All right, and in fact, we have the others, but I just want to let you guys know, M1 follow the can down notation. So you can look up can down notation, and then you can have the full understanding about the can down notation, and so that we will have the M1. And in fact, if we want to have the further description, in fact, we should have the fourth one. The fourth one actually called capacity. All right. And for MN1, actually, we can have another notation, MN1 with infinity for the fourth position. Infinity, so we have the capacity of infinity. If we have the capacity of infinity, what that means? Here we should have this. Infinity, so we have a buffer and we have a single server. So buffer is 1. That says we should have server is 1 and the buffer size should be infinity so that the capacity include the number of servers. and also the buffer size. Let's say if we have mn1 infinity, this one should be the clear description for the system, but we skip infinity, and so that we have the reduced notation, and that is the mn1. And furthermore, you can have another one to have the service discipline. And the same if we have first in, first out, FIFO, first in, first out. And also we can skip the description for first in, first out. So simply we have mn1 infinity, or simply we have mm1. All right, so the countdown notation mn1 here indicate such a system. Okay, such a system. So we have mn1 to be studied in the following programming codes. Well, about the mn1, and right now we want to know if we want to have the exponential. This one, in fact, it is an exponential. So if we have a uniform first. All right, so this is a uniform. You can use, for example, the library of C programming language, and so that you can find a function uniform. And the uniform that you have a value for in between 0 and 1. For example, you may have 0.1 from the library of the programming language. And actually, in the following, we can have actually not from the library of C programming language. We can have our own source code to describe how to generate uniform. All right, so first of all, we assume we can have the uniform, the value for in between 0 and 1, and indicate by U. All right, simply U. So this one, it is the first step. And the second step, we can apply the function. All right, we can apply this function. If we apply the function minus beta and taking the logarithm with respect to this random value U, and then we can have a random variable. In fact, if we want to have the name for this random variable, it's an exponential. It's an exponential random variable. And we have a mean beta for the exponential. Well, what is the meaning beta for exponential? Actually, you can use Google to find exponential random variable first. And then later we can find the probability density function, not generating, probability density function. And later we have such a function, but what is the form? So that's why I ask you guys to use Google if you don't have any idea. So you can use Google to find exponential, and then you may have the formula for the probability density function. So right now, we use the current page, this page, to let you guys know if we talk about exponential. Okay, an exponential with a mean beta. If we have exponential with a mean beta, you guys can use Google, or maybe you can use chapter. Chapter 6. You can refer to chapter 6, and then you can have the formula for exponential. First of all, we want to know exponential. Exponential with a probability density function with this form. All right, so PDF with the form. And in fact, you should have the definition for CDF. So you can look at this. It's the results in chapter 4. Or maybe right now, you can understand what that means, CDF. Cumulative distribution function, CDF. All right, so that's a CDF here, F. So F follow these. If we have a random variable, by getting the probability for this random variable lower than or equal to the specified variable small s. Okay. All right, so first of all, we need to understand the meaning probability density function and cumulative distribution function, actually capital F of x. If we have a PDF, and also we can derive CDF, then we use the current way to derive CDF for exponential. All right, exponential with this formula, but what is the range? In fact, the range is this one. X, the dummy variable should be non-negative range. If we have the non-negative range, actually, what is the range for the integral from 0 to the current value x? Because we try to understand the possible value for non-negative only. If we can do so, then you can get the results for CDF. It should be 1 minus exponential raised to the power to minus x over beta. So this is the first step. This is the first step. For the first step, it says, for exponential, you can have the form of CDF. And the second one, right now, we want to check the previous given random variable, minus beta, multiply log u. And the same, we try to get the CDF. But the CDF here, do you think this is the specific random variable? It should be, but right now, this is the CDF for this one, but right now, no name. Okay, for the first for the first step, we obtain the results. It is a CDF of exponential. But right now, minus beta multiply log u. Currently, we call no name for the random variable. Okay, right now, we may think no name associated with the current random variable. But we still want to know what is the form for the current CDF. You can call no name random variable CDF. And follow this, so you can rearrange it, right? And furthermore, you can rearrange it. And finally, this one, it's uniform. So uniform, actually, you should have the range. And right now, greater than this. So finally, we can change it to exponential raised to the power to minus x over beta. And another endpoint should be 1. So that's why you have the 2 endpoints. With the 2 endpoints, it's a uniform. So how to have the results? It says for in between the range. It's really easy. So we try to find the distance because uniform. So we can use the distance to measure the probability. So finally, we should have 1 minus exponential raised to the power to minus n. All right. So this one we have the second step. For the second step, it says CDF of the no-name random variable has the form 1 minus exponential raised to the power to minus x over beta. Well, right now, no name with the form here. And the form here the same as exponential. So what that means, it says this no-name random variable should follow the exponential random variable because they have the same CDF, the same form of CDF, so that if we don't have any specific reason why we choose the function, but if you are asked to check why the current random variable follow exponential, you can use the current page to understand, yes, it should follow the exponential random variable because they have the same form of CDF. Okay, so I think you guys should understand me, right? So up to now, any question? If no, let me get back to the discussion here. So it says MM1. It is a specific system. And we want to know exponential. So it says the task force someone tried to, the task force somehow tried to use the current way. If I let you know, we can use the library, or maybe we can have a specific function to find uniform. And then we can apply the function minus beta log u to generate the exponential random variable. And the next page actually that you have the reason. And so that you can believe the current function actually can that you generate the exponential random variable. If you can generate the exponential random variable, that says you can use the current function to generate inter-arrival times. And you can use the current function to generate service times. Well, about the inter-arrival time and service time, in fact, they are independent. So you can use the same function but different parameter, and so that you can have the description for inter-arrival times and description for the service times. And almost so, because M1 here, right now you can specify M for the first M and also specify for the second M. And finally, you have the fixed one, single server, and almost done. But how to do for the remaining? In fact, we know MM1. We try to achieve the description for the system MM1. And also we know M, how to generate M and the second M. And in fact, we have the remaining to do. We need to write a simulation program. And in the following, we use C programming language. For the C programming language, actually, we have the following program modules. We have initialization. We have timing. We have arrive, depart, and report. And actually, we have a main. Right? So we have these. And we try to, that you guys know how to have the program for these modules. And also that you guys feel why we should have the way to describe these modules. So let us use following routine. Actually, the flowchart for the following routines. First of all, we try to use a routine to describe arrive. And next routine, it should be depart. And also, we may have the other routine, but we try to focus on the main routines. First of all, this is a routine for arrive. And right now, that you guys have these. Arrive here. So we should have arrive. And arrive, what that means, if we have the arrival event, well, this is arrival event. And in the following, this is a detail for the arrive, the module of arrive. If we have an arrival event, for example, right now, this is a time axis, arrival. And then you should understand if this is the time axis. So you may have the next one. So that's why you schedule next arrival event. Well, why? Because we use the event driven. So we use the event driven. Therefore, we know the first arrival, and then we code the next arrival. All right, something like we code the next arrival, and then we can stop because no need to have the next one and next one and next one. So we simply have a single next one because we can code one by one. All right, so if we have the arrival, we code simply the next arrival and no need to code a batch of arrivals. We code simply the next arrival. And furthermore, maybe you have a question. Why not batch? If we have actually, if we have M, so it should be exponential inter-arrival times. And exponential means per zone. So previously, I do not mention this, but in fact, for the arrival with the exponential inter-arrival, in fact, we should have the per zone arrivals. So in fact, we have the input per zone. All right. So the same, you can use Google exponential inter-arrival times so that you can find you should follow per zone arrivals. So the formal name actually you should call per zone arrivals. Per zone arrivals with the exponential inter-arrival times. And that's it. So we can call per zone by using the exponential inter-arrival time, and then we can get the next arrival event. All right, so if we have the arrival, and then we can schedule the next arrival. This arrival somehow like serve as the standby arrival because right now you should process the current arrival, but you call the next one to serve as the standby event, standby arrival event. And then we can check because we have the current arrival, this one. And this one, somehow like it is a standby. Standby event, arrival event. All right, so we can call the standby next arrival event, and then we should check for the current arrival. We should have the proper arrangement. So we should check, is it current arrival can, I mean, is it current arrival entering the server? Or it should be put into the queue. All right, so we check, is the server busy or not? If the server is busy, so put it into queue. If the server is not busy, so enter servers. Here we only have a single server, so we have the server, enter server. All right, so we have 2 branches. But before I have the further discussion, let me erase the current discussion. All right, so this one, enter the queue. This one, server. So let's check the step for entering the queue. About entering the queue, you can check these. Because entering the queue, so you try to increase number in queue. So that says you increase the queue size. And also, you can skip this one currently. You enter the queue, but you need to store the time of arrival for this customer, right? So that says previously about the snapshot, you should have the array to store time of the arrival of the customer, right? Well, formally, you should go follow the stream here. Once you have the update for number in queue, you should go to this. You should have the array to store so that you have the array to recode the arrival time instant for this customer. And then down for the left-hand branch. But while we have the current one, queue is full. Remember, previously we have the infinite size, right? Well, in the following, we use array. So if you use array to implement buffer, so can you have the infinite size buffer array? Actually, no. You cannot have the infinite size array. So you should employ the finite array. Well, if you employ the finite array, what is the size should be associated with the current buffer? In fact, you try to choose large enough. Large enough size for the array, so that you try to use this one to approximate the infinite size buffer. Because of this, you choose array, and so that you have the large enough size. However, it should be the limited size. So you still have the case. Is the queue full? If you have the case and you reach the full queue, and then what that means? Something wrong. So you have an error message and stop the simulation. Why? Because you run the simulation to simulate the MN1 system. For the MN1 system, you cannot have the full buffer size. Okay, no full buffer size because you have the infinite size of a buffer. So you cannot have a situation like that. However, we use a finite size array to implement the queue. So we may have a situation like this. So if you have a situation like this, then you should have the exceptional case. The exceptional case that will stop the simulation because not okay if you have the full buffer. If it is not the full buffer, that says it should be the normal case for MN1. So somehow like you can bypass the current situation and so they go to the normal step to store the time of arrival, and that's it. All right, so this is the left-hand side branch. We have the step to join the queue. And join the queue, you have the exceptional case to process. So you need to check, can we have any unacceptable case if we have the situation of a full queue. If we have the case of the full queue, then we need to have the error message and stop the simulation. All right, so this is the discussion for the left-hand side branch, joining the queue. And let us check the right-hand side branch to talk about entering the queue. If you have the arrival, and this arrival C, idle queue, idle server. The arrival sees the idle server. And then is it okay to allow the customer to enter the server directly? Yes, it is possible to allow the arrival to enter the idle server because enter the idle server. So how about the queuing delay? Here I have the actual world queuing delay. So you can set queuing delay to 0 as the discussion done previously, maybe 2 weeks ago, with that you guys know, if we allow the customer enter the server directly, and then it says 0 queuing delay. So that's why we set the delay to 0. Here the delay means a queuing delay. So that's why we have a 0 for this delay. All right, so if we allow the current customer to enter the server because these customers see the idle server, so we have a 0 queuing delay. And maybe you can have the other thing to do to gather some statistics. But right now, we simply focus on delay is 0. Perhaps you need to update the other statistics. But right now, we keep it simple. We may have the other subroutine to update the statistics. But right now, we don't have the further discussion. If we have the queuing delay, and maybe you can have the other updates. But right now, we don't have that function to that you guys know, and later we will talk about that function. Yes, if we focus on queuing delay, and right now we know this queuing delay for the customer, so we can have the increased sample size. The increased sample size called number of customer delay, so we can increase the variable by adding it to, by adding 1 to the current variable. So that's why add 1 to the current variable. All right, so this about the queuing delay, about the sample size. The sample size for the queuing delay. And furthermore, because this customer occupied the server, so we can change the status from idle to busy. Well, up to now, it says you can occupy the server, so you can understand the server will serve the customer, and you will estimate, actually not estimate, you will schedule the departure event for the customer, and so that you have the possible departure time instant. But right now, not the current event, because you may choose the other event by following the snapshots. Right? Again, we finished the discussion for the right-hand side branch, talking about the customer joining the server. If we finish the 2 branches and then we finish the routine for arrive. And that's all. Up to now, I think you guys understand for the MN1. And also we need to have some routines. At this moment, we finish the discussion for arrive. And let me stop here and asking you any question about the current discussion? If yes, let me know. If no, of course, we still have a few minutes before the cross break. And we will continue to discuss the next event, depart. Again, let me ask you any question? If you don't have the question, so we may have the next event, actually the next main event, depart. All right, so the current flow chart that you guys know, departure routine. From the previous discussion, I think you guys understand we can schedule the departure event if the server becomes busy. It doesn't mean right now we should process using the previous arrive routine. It doesn't mean once you schedule the departure event and then you should process that departure event directly. But once you reach the selection for the departure event, somehow like you select the next event to be the departure event, and then we have the routine here, depart. Yes, if we need to process the departure event, and then we need to think about departure. So it says the current customer should leave the current system. Once leave, and then it looks back the system to check the queue. The queue empty? Oh, the queue is not empty. If the queue empty, it says no other customers in the queue. So no need to allow the server to be busy again. So we check it to the status idle. And once you change the status of the server to idle, and then you can allow the customer to leave. Allow the customer to leave, so that says you can eliminate the departure event because everything's done. Although it leaves, you need to have the other possible update. But right now, if you care about queuing delay, then no need to care about the further discussion. You simply allow the customer to leave. And that's done. So that's why we use the term eliminate. All right, so this is a left-hand side branch. If we have the empty queue. If you don't have the empty queue, right? This is a right-hand side branch. And then what to do? In fact, you try to get the head of line. Head of line. let's say it's the first one in queue. So you tag the head of line. You need to tag head of line to allow that one to enter the queue. So you need to subtract one from queue size. And also for this head of line, you can calculate the delay, the queuing delay. So head of line means the current customer entering service. That says entering the server. And the same, you may have the other terms. But right now, we skip the other term by using gather statistic. And later, we can have the update statistic to fulfill the current function, gather statistics. All right, so up to now, we should take head of line. We understand the head of line queuing delay, so we can compute delay for the customer entering the server. That says the head of line with the known queuing delay. The same, because we understand we can get the delay, the queuing delay for the current customer. So we can increase the sample size. And again, similar to the previous one, entering the server directly. So we should schedule the departure event. Look at this. Schedule the departure event. Well, for the previous one, schedule the departure event and then that's done. But right now, for the current process, we should have the actual one. This is the head of line. And the head of line enter server. So you should remove this. If we have, because previously we have the way HOL here, using the vertical way to describe the system. So it says we need to move the other customer, move them up, but move them up one place. So that's why it says move each customer in queue. Move up one place. So that says for the current one to this, and for this one to this, and the other one to this, all up one place. And then you can allow them to have the new position to queue. Okay. All right, so this is a depart. And if you don't have the empty queue, and then you need to get one from the queue, that says get head of line from the queue. And then you need to compute the delay for the head of line and try to get the sample size and schedule the departure. And also try to update the array by moving up the customer one place, actually for every customer, by moving up one place. And then that's all for the depart. Okay, so this is the description for the routine depart. Maybe we have a few minutes left to have the cross break, but still the same, we can allow you to have a 5-minute break. All right, up to now, any question? If no question, let us take a break. And 5 minutes later, we can restart by checking the next page. Okay, take a rest.